Welcome to structural dynamics class. So far we have studied the solution of dynamic equilibrium equation, first in classical manner, and second we have studied that in the Duhamel's integral way of solving it. So if any arbitrary force is acting on the structure, then we have studied the response. So in two way, one is classical by decomposing that into sine, and then Duhamel's integral by decomposing that into a series of impulses. So now we are going to study Fourier transform method. So how do we use transforms and convert the differential equation into algebraic equation and solve it? So before going into the transform method, let us first understand what is a Fourier series and how earthquake excitations act, how earthquake is exciting the building, and then how do we write the equation of motion for that, and then finally the solution of this dynamic equilibrium equation in frequency domain. First let us discuss earthquake excitation. So earthquake excitation is, like, say, assume that this is a structure. Earthquake excitation means force is acting, that is excitation, ground is exciting. So ground is vibrating like this. So when ground is vibrating, so you can see that because of this ground motion, so ground is moving and structure is vibrating here. Okay, so ground is moving and structure is vibrating here. So if you look at this closely, if you look at this closely, what is actually happening is, in this one you can see UG is the ground displacement. So this part is moving up to this part. Okay, so this ground is displacing from here to here. This is UG, ground displacement. And then when the structure, base of the structure is stopping here, mass is not stopping there, it is going further. So that is UT, that is the displacement of mass. So the total displacement measured from this part is UG plus UT. Okay, it is total displacement is UG plus U. So UG of t plus U of t. So velocity, if you differentiate it once, we get u dot g and u dot g and u dot, and acceleration is u double dot g and u double dot. So now let us write the equation of motion in this condition. So equation of motion is the acceleration, mass is related to the acceleration. So inertia force is related to movement of the mass. So mass has moved from this point to this point. So that means inertia force should contain these two terms, that is u double dot g as well as u double dot. Whereas the stiffness force, if I explain you, like if base has moved 3 centimeters and tip has also moved 3 centimeters, so the force in this one is 0. So because there is no relative displacement between these 2 points, so it is 0. So that means what? So for us to calculate the force in the column, we need relative displacement. So that means what is relative displacement? Relative displacement is the displacement between base and the center of mass. So that is only u, even though the mass has moved from this location to this location, new location, the mass has moved from here to here and base has moved from here to here. So that means relative displacement can be calculated something like UG plus U as the tip of the mass, motion of the mass, minus UG, so which is equal to U. So this is U. U is the relative displacement. Okay, so stiffness force is related to relative displacement, inertia force is related to absolute acceleration, damping force is related to relative velocity. So if we write the equation of motion, it looks like this: inertia force, damping force and stiffness force. So then if we rewrite this equation, mu double dot plus cu dot plus ku is equal to minus mug double dot. So that means what? Earthquake force is nothing but mass times ground acceleration. So like this UG is actual main component of earthquake force, u double dot g is main component, which is earthquake excitation itself, and mass is the component which is which may increase or decrease. So if mass is higher, force is higher; if mass is lower, force is lower. So that is why it is said in earthquake engineering that lighter mass attracts lower earthquake forces, heavy mass attracts higher earthquake forces. So earthquake force will be induced at the center of gravity of any body. So the induced force is this, that is inertia force is the induced force, or earthquake force is the induced force. Now let us discuss Fourier series. So how we make use of this Fourier series in Fourier transform, and then how we make use of Fourier transform for finding the solution in frequency domain. So first let us discuss briefly a Fourier series. So Fourier series is any function can be expressed in terms of sum of series of sine functions and cosine functions. So you can see this a force or displacement or any signal f of t can be represented like this. So a0 is constant, so a1 cos omega 1 t, a2 cos omega 2 t, like that series, and sine. So this up to n, so n can be any number, it can go up to infinity also. So whereas omega 1 is as small frequency as possible, that is 2 pi by say t. So t is very small component, okay, and omega n is n times 2 pi by t, that means n omega 1 is a frequency. So this omega 2, omega 2, omega 3, omega 4 can be represented in terms of this. So they are all linked with omega 1. Omega 1 is a small quantity, as small frequency as possible. So in that case we can represent the entire function something like f of t a0 by 2 plus summation of n from 1 to infinity an cos omega n t plus bn sin omega n t. So the any function can be represented in the form of series of sines and cosines with this summation form. So now, so let us go further. So any function can be represented like that. So let us understand the properties, okay, and then we need to find out what is an and what is bn, which is coefficients. So if we multiply both sides, left side and right side, by cos omega n t and also sin omega n t, and integrating over one period, so one cycle, so what we are going to get? So this is half cycle, so that is t by 2, and this is another half cycle, so minus half to plus half, this is one full cycle. So if we integrate it over one full cycle, that coefficient value is that the product value is the an t by 2. Similarly in sine also bn t by 2, because it is multiplying with this function. Now an will be 2 by t into this one, bn is 2 by t into this function. So in if we sum the cos sine multiplications of cos multiplications of sine over one period, what values we will get? If you look at this one, a by 2 sin omega and t is equal to 0. So how it is 0? So if you take say one sine function, if you add up all values, so this total value is positive, this total value is negative, so both if you add, summation will be 0. Now in this case, say cos and sine both multiplied together and then adding. If I draw this say cos function, this is cos function, and then if I draw say sine function, sine function is something like this, something like this. So this peak is here, this peak is here, and this peak is here, like this. So if we look at this one, okay, so if I say call this as A, this as B, this as C, this as D, okay, A, B, C, D kind of thing. So you can see these values, so their values are same, but so signs are different. So you can see this one, this is positive, this is positive, so both will become positive, and this is positive, this is negative, negative. So this is negative and this is negative, this will become positive. So this is negative and this is positive, will become negative. So if we add up this multiply by this multiply by this multiply by this multiply by this, and add it up, we will get 0. So, but whereas in this case, if you take another sine function, So you can see this one, this multiply by this positive value, this multiply by this again positive value, this multiply by this negative negative again positive value, this multiply by this again positive value. So that means sine function multiply by sine function integrated over the period is non-zero, and sine function and cos function integrated over the period is 0, and only sine function integrated over the period is 0, only cos function integrated over the period is 0. So that means, so this has value, Bn has value, An will be coefficient will be 0. So this value is 0 and this value has some this has non-zero. Okay. Now let us look at the diagrammatic view of this frequencies. Okay. So if you can look at this signal, so it is a sinusoidal series, signal 1, this is sinusoidal series signal 2. So in this one you can clearly observe that this signal and this signal has different frequencies. So this is signal 1 having omega 1 as frequency, this is signal 2 having omega 2 as frequency. Now if we add this omega 1 signal to omega 2 signal, both signals will be there. As you can see this one, two signals are included in this signal. Now if we take the Fourier transform or Fourier amplitude spectrum of this one, we get peaks at one frequency, peak at this frequency. That means what? Fourier transform is telling us that what kind of frequencies are present in any signal. So now how do we get from here to here? So this is a time series and this is a frequency domain function or frequency domain chart or the spectrum. So how do we get from here to here? Let us discuss that. So like A0 by 0, that is a signal which is represented in the form of series of sines and cosines, summation of cosines and cosines. So this cos omega, omega nt, sin omega nt can be represented in the form of exponential functions. So now if you substitute cos and sine in the form of exponential functions in this one, so and rewrite it, so we get Cn, which is a constant term, coefficient term, and Cn conjugate. So this is a coefficient term on the conjugate side. So like the both things can be added and can be represented in the form of Cn 1 by 2 An minus Ibn. Okay. So Ibn is a imaginary part. So An and Bn we already know. So if we substitute An and Bn in this equation and evaluate it, so we get Cn value. So we can write f of t is equal to summation of minus infinity to plus infinity. So this is minus infinity to 0 and this is 0 to plus infinity. So 0 to plus infinity, minus infinity to 0. So both added together we get one constant one single term Fourier series, and then Cn can be evaluated like this. So if you back substitute it, okay, then what we get is something like this one. So an earthquake signal which is repeating after say the entire signal period. So something like this is a random vibration and this is repeating after every cycle. So when the total time tends to infinity, so we can assume that each earthquake signal is continuously repeating. So then t is 2 pi by omega n. So if we substitute this and omega tends to omega w and d omega tends to very small value. So then if we find the limits of that for evaluating Cn, so Cn will be 1 by 2 pi minus infinity to plus infinity double integral of this function. Now from this we get this ft, if we substitute this one, so 1 by 2 pi minus infinity to plus infinity f of omega e to the power of I omega nt d omega, and then next one is f of t 1 by 2 pi minus infinity to plus infinity ft into e to the power of minus I omega n t, this is dt. So in this one, so this is a Fourier transformation pair. So Fourier transformation states that any time signal is available to us, so we can convert that into frequency domain by putting here time signal, and any frequency domain signal is there, you put that in this place and convert that into time domain signal. So frequency domain signal can be converted into time domain signal, and time domain signal can be converted into frequency domain signal. Now let us discuss response of structures in frequency domain. So the methodology is as follows. So this is a structure which is having mass, damping and stiffness. So three parameters: mass of the structure, damping of the structure and stiffness of the structure. If we give input ground motion to this structure, then we get response of the structure in time domain. So how we get that is mu double dot plus cu dot plus ku is equal to p of t. So input motion is given here at pt. So this is a acceleration, can also be called as u double dot g, and this pt is p of t is equal to m into u double dot g. So mu double dot plus cu dot plus ku is equal to p of t. So we have discussed and understood how to get the response, okay, to this one. So response is ut. Ut is a displacement response, u dot t is a velocity response, and u double dot t is a acceleration response. So we can solve this one and get ut. But now how to get this in frequency domain? So that is what we are discussing. So if we convert this time history input ground motion using Fourier transformation pair into frequency domain. So if I show you the previous this one, so that time signal, that force, if we input here, then we get force in frequency domain. So that's what is required here. And then this response of the structure, if you convert that into, again put this in the Fourier transformation pair, we get response here. Okay. Now instead of that, how to get? So this is the input ground motion in frequency domain. This is the output response in frequency domain. So this is Fourier. So how do we get from here to here directly, instead of doing this one? Instead of doing, say, input time history and get output time history, instead of that, how to do from frequency domain to frequency domain? So that is what we are going to calculate. So this is equation of motion. So mu double dot plus cu dot plus ku is equal to p of t. So the dynamic equilibrium equation. So first term is inertia force, second term is damping force, and third term is stiffness force, and all put together is equal to the external force. So we need to convert this external force into frequency domain. So by using that Fourier transform pair, so this pt we put at the time function and then convert that into frequency domain. So it is something like this. And so this is the right hand side, and the left hand side all terms. So we convert that, we apply here. So minus infinity to plus infinity, mu double dot e to the power of minus I omega nt dt plus cu dot e to the power of minus I omega nt dt and ku. So all these three terms. So now this ut is a time domain function, u dot t, that velocity is also in time domain, acceleration is also in time domain. So we need to convert each function into frequency domain. So this is how it is done. So the first term, that is stiffness term, is getting converted in frequency domain. So we write that as stiffness, okay, u cap function of omega, and mass term minus m omega square u cap omega, and then damping term is converted like this, c omega n u cap omega. So this is also omega n. And then if we combine all these three things into equation, that is p cap omega is equal to minus m omega n square c omega n plus k multiplied by u cap omega. So from this we can get so the response in frequency domain by giving input in frequency domain. So here you can clearly see this is a time history, this is the equation of motion in time domain, and this is the response of the system in frequency domain. So here we have converted this differential equation into algebraic equation, and it is very easy to find out the solution in this form. Summary, what we have discussed in this class. So first we have understood how a signal can be decomposed into a series of sine and cosine functions, and how a signal can be converted from time domain function into frequency domain function, and later we have understood how to solve the dynamic equilibrium equation which is in the time domain into frequency domain. So in Fourier transformation method of solving this dynamic equilibrium equation, we convert differential equation into algebraic equation and solve it.